Since the beginning of time, mathematicians have used real-world objects to assist in their calculations. After all, what better stepping stones for early mathematics than nature itself? But just as how the very thought of a square occupying negative area made no sense, mathematicians could have never come up with something as irrational as going beyond the world's three dimensions. It wasn't until Jean Laurent d'Alembert, a French mathematician who first thought of what would happen if we added another dimension, and Charles Howard Hinton, who popularized the insights of 4D objects such as the tesseract, that 4D research took off. Today, we are not looking to delve into very complicated higher dimensional mathematics, but rather to just get our feet wet by exploring a fun puzzle. How do we calculate the volume of a 4-dimensional sphere, also known as a hypersphere, using our 3-dimensional brains? To do this, we will first simplify the problem to lower dimensions and then work our way up to the 4th dimension. This line here represents one dimension. Let's say Linus the Linelander lived on this one-dimensional line. To Linus, this line is his whole world, so he would only be able to move left or right. If he tried to move up or down, he wouldn't be able to. So we can see that the entirety of this one-dimensional world is defined by a single arrow pointing to the right, called the x-axis. Now, let's upgrade from this one-dimensional world to a two-dimensional world that we can call Flatlandia. To do this, we just need to add a second axis, but with the special rule that this new axis is perpendicular to all the axes already present. We call this the y-axis. As you can see, these two axes define a plane called Flatlandia. Frank the Flatlander is a circle moving around in Flatlandia. Now, what area does Frank occupy? There are actually a number of different ways to do this, but let's remind ourselves of the ultimate goal here. We want to calculate the volume of a 4-dimensional hypersphere with our 3-dimensional brains. So similarly, we should be looking at how we could calculate the area of a circle if we were thinking in one dimension. So let's go back to Linus and see how we could approach the problem if we lived in a one-dimensional world. First things first, how do we even visualize a circle in one dimension? Is there any way you could get an idea of what a circle might be? You give it some thought, and after thinking for a while, you come up with an idea. You tell Linus to go online, no pun intended, and message Frank to move through your one-dimensional line. Frank obliges, and now you can see a line suddenly pop into existence. It starts to grow until reaching a maximum length equal to the diameter of the circle. The line then starts shrinking until it disappears. Do you see what we are doing here? We are using time as the second dimension to visualize the circle. Based on what we just saw, we can divide the circle up using straight lines, where each segment has a base of a straight line with a very small thickness. This thickness is in the direction of the time axis and can be represented as delta t. Since the segments are very thin, we can actually approximate them to be rectangles. The area of each rectangle, or as we like to call slice, equals the base length L multiplied by the thickness delta t. We can also say that the sum of the areas of these slices equals the area of the circle. Or actually, it approximates it since there is some error. But as you can see, by increasing the number of slices, the error becomes smaller, and so the sum better approximates the area of the circle. In fact, if we segment the circle into an infinite number of slices, each with infinitesimal thickness called dt, each segment will actually become a perfect rectangle with sides dt and l, and will hence have an area of l dt. Since there is no error this time, the summation will now actually equal the area of the circle. Finally, we can replace this summation sign with an integral sign. If you haven't taken calculus, don't worry, just think of this squiggly line as a function that divides the circle into an infinite number of segments, such that each segment is now a perfect rectangle, and then adds up their areas to get the area of the circle in a process called integration. So now that we have an integral representation of the area of a circle, all we need to do is represent the integral in terms of t, so that we can perform the integration. To do this, let's take a random strip on the circle. T is the distance from the origin to the center of the line. Remember that this is along the time axis, because as you'll recall, the axis through which we pass the circle through the one-dimensional world is the time axis. Now we draw another line, which we know to be the radius of the circle. Since this entire length is L, we are now interested in finding this length, L over 2. Now it may be tempting to use the Pythagoras theorem to get L over 2, but that will actually make the integral quite complicated. So instead, let's define an angle theta as shown from the positive x-axis. The angle inside the triangle is now 90 minus theta, and using some trigonometry, we can get that L equals 2r cosine theta. Since we are expressing the length in terms of theta, we need to do the same for dt. Since we can see that t equals r sine theta, by differentiating both sides, we get that dt equals r cosine theta d theta. So the integral is now 2r squared cosine squared theta d theta. Finally, we need to insert the bounds. Remember, the angle is defined to be between the positive x-axis and the radius line we have drawn. This means that the angle changes from minus pi over 2 to pi over 2 radians. If you aren't familiar with definite integrals, you can think of these bounds like the bounds on a summation sign. We are summing the areas of all the rectangles from when theta is at its minimum value of minus pi over 2, where the rectangle is at the bottom of the circle, all the way until theta reaches its maximum value, pi over 2, when the rectangle is at the top of the circle. In this way, we have summed the areas of all the rectangles in the circle. Now we can evaluate the integral to get that the area of a circle equals pi r squared. The integration technique itself is not important, but I'll flash it on the screen if you're curious. Now that we've calculated the area of a circle, let's go into 3 dimensions to find the volume of a sphere. So firstly, we need to add an axis that is perpendicular to both the x and y axes. We can call this the z-axis. Now, let's say we have a sphere in this 3D world. How do we calculate its volume? Remember, in the case of the circle, we passed it through a one-dimensional line, where we used time as a second dimension to view it as a line that grew before shrinking back down. With this in mind, how would you visualize a 3D sphere if you lived on a 2D plane? Well, you could pass the sphere through the 2D plane. Then you would see a circle emerge that kept growing until its radius was the same as that of the sphere. Then, the circle would shrink back down. In this way, we are using time as the third dimension. Now, we can see that the sphere can be divided into slices that look like cylinders, each with a cross-section of a circle and a small thickness delta t. And if we divide it into an infinite number of segments, each with thickness dt, then each slice will be a cylinder exactly. So to get the volume, we simply need to sum, or in other words, take the integral of the volume of each cylinder segment, which is given by the cross-sectional area times dt. The cross-section is simply a circle, so we can represent this area as pi r squared. Well, actually, since we refer to the radius of the sphere as r, let's refer to the radius of each circle as L, so the area can be written as pi L squared. Now, the manipulation of this integral is very similar to the last case, but we need to look at a vertical cross-section of the sphere to perform it. We can see that the radius of a slice, L, can be written as r cosine theta. Next, Since t equals r sine theta, we know that dt equals r cosine theta d theta. Let's also take a moment to remind ourselves that the strips are not rectangles, but rather cylindrical slices that have a circular base. Finally, as this animation shows, the bounds are still from minus pi over 2 to pi over 2. Subbing this all into the integral, we get that the volume of the sphere is given by the integral of pi r cubed cosine cubed theta d theta, with bounds minus pi over 2 to pi over 2. Evaluating this integral, we get that the volume of a sphere is 4/3 pi r cubed. Finally, let's venture into the four-dimensional world. To do so, we just need to add another axis that is perpendicular to all the other three axes. But unfortunately, that isn't possible, at least for us to comprehend. You see, since we live in a three-dimensional world, our minds can't visualize four axes that are all perpendicular to each other. However, luckily for us, we don't have to. We can simply use the method that we used previously, of using time as an extra dimension to visualize and perform calculations on this hypersphere. But first, a quick review of what we did for the lower dimensions. For a 2D circle, we passed it through a 1D line and saw it as a line that changed in length. For 3 dimensions, we passed a sphere through a plane and saw it as a circle that had a changing radius that increased till it reached the same radius as the sphere and then decreased back to 0. With these examples in mind, what would you expect to see if we passed a 4D hypersphere through a 3-dimensional world? We would see a sphere that has a changing size. The radius of the sphere would first increase until it equaled the radius of the hypersphere, and then shrink back down to 0. This means that if we were to represent the hypersphere using a 2D circle, where the vertical axis is time and the horizontal axis represents the 3 spatial dimensions x, y, and z, then each slice we obtain would be a sphere of radius L. If you're having difficulty wrapping your head around this, perhaps this representation will help, where we see spheres of changing radii along the time axis. The volume of each slice is 4/3 pi L cubed times dt, and the volume of the hypersphere is calculated by summing up all these volumes using an integral. The radius of each sphere that we have denoted as L can again be given by r cosine theta, and since t equals r sine theta, we see that dt equals r cosine theta d theta. Subbing in the variables, we get that the volume of a hypersphere is given by the integral 4/3 r to the 4 cosine theta to the 4 d theta from minus pi over 2 to pi over 2. And after some calculations, we finally arrive at the conclusion that the volume of a 4-dimensional hypersphere is given by half pi squared times r to the power of 4. Let's take a moment to appreciate just how amazing this is. We managed to find the volume of an object that we can't see or even visualize. That is the power of mathematics. By simplifying the problem to lower dimensions, we were able to find a method that could be transitioned up to higher dimensions. In this way, we could use the intuition gained from solving the simpler cases to guide us in tackling the monster that is the 4th dimension. Pretty elegant, don't you think?